Hi everyone, hope you all are good. So, we are here for grade 9 math. So, we are working on the book Nelson Principles of Mathematics, grade 9. We're working on chapter 6, that is investigating relationships. The lessons we're going to cover today are reasoning about data, at describing situations from graphs. So, let's just start with the lesson 6.4, that is reasoning about data. Okay. Quote or reject a conjecture about a relationship by examining trends or patterns in the data. You may see a trend or pattern in plotted data, however, more detailed data might not support your original conjecture. If a trend or pattern in the data agrees with a conjecture, then the data supports the conjecture. If there is no apparent trend or pattern in the data, or there is trend or pattern and it contradicts the conjecture, then the conjecture is not supported by the data. Conjectures made from datasets that contain a small number of observations may not be valid. The larger the number of observations made, the more likely the trend you see is valid, right? These are the key points from the lesson. So let's just start with the practice questions. Okay, the question is Natali collected this data from the height of 14-year-old girls and their mothers. Okay, plot the data on a scatter plot. If possible, sketch a line or curve of best fit. Is there a relationship between the variables? Okay. Okay, let me find a tool to plot a scat to so that I can plot a scatter plot, right? Okay. Line tool for scatter plots. Because all of the questions need a plot, scatter plot. Okay, let's start this one. Scatter plot. I'm going to plot the scatter plot here, right? Okay, here is the data 1.6 to 1.55. 1.6 to 1.53. 1.53, 1.51, 1.53, 1.51. Okay, 1.58, 1.76, 1.58, 1.76. 1.62 and 1 point. Okay, 1.59, 1.53, 1.59, 1.53, 1.49, 1.53, 1.49, 1.51, 1.71, 1.51, 1.71. Okay, let me just add another values. Okay, 1.55, 1.55. Okay, 1.55. You don't have to put comma between them. 1.55. Okay, 1.57, 1.61, 1.57, 1.61, 1.68, 1.75, 1.68, 1.75, 1.62, 1.56, 1.62, 1.56, 1.54, 1.56, 1.56, 1.54, 1.61, 1.54, and 1.61. Okay, draw. Here is the scatter plots, right? These are the values. Okay, so we are done with the scatter plot. Now what you have to do for the B part, you have to, if possible, sketch a line or curve of best fit. Okay, you can see we have already a line that is best fit, right? Okay, let me see from where can I draw a. Okay, you have this one. Okay, the C part is if there is a relationship between the variables, if so, describe it. Okay, you have to see the relationship between these the variables, right? Okay, you can see. Okay, you can see the values. The Y values are increasing 1.55, 1.57, 1.61, 1.68, like, right? That means the girl's height are increasing. That means the values are related, right? Okay. Okay, let's just look at question number 3. Research suggests that there is a relationship between age and vocabulary size of young children. Explain how the following data can be used to support that statement. Okay, you are given a data, you have to see if the data supports, like, as age increasing, the vocabulary of the children's are also increasing. Like when if they are 1 year, they can just 10 words. In 2 years, 450 words, right? So basically, we need to make a graph for the data, right? So age is the independent variable here, right? Vocabulary size doesn't depend on age. So age is an independent variable. So we have to make a scatter plot that represents the x and y values, right? Okay, so let's just make a scatter plot of the given data. Okay, let me just make a plot. 110 to 450, 110 to 450. Okay, 3000, 3004 to 500, 3000 to 500, 1000, 4 1150, I think, 4 1150, 4 3000, 3 1150, 3003 1150. Okay, 4 1400, 4 1600, 4 1400, 4 1600, 5 2000, 5 2150, 5 2000, 5 2160, 50, 6 2400, 6 6 2400, and 6 2750, and 6 2750. Okay, let's just draw. Okay, this is the best fit line, right? You can see the clear trends. You have so many points on the line. That means you have the trends in the data. That means the data can be used to support the statement in this way, right? Okay, let's just start with question number 6. Suppose that you collected data on the total length of road in Canada for past 100 years and the incidence of cancer for the past 100 years. If you plotted the data on a scatter plot, what would you expect a line or curve of best fit to look like? If two variables are related by a line or curve of best fit on a scatter plot, does that mean that one of the variable influences the other? Explain. Okay, that means I I would accept the conjecture if the set of data I'm analyzing seems to support the conjecture, right? That is, if the data points and the graph all point toward the conjecture being without a shadow of a doubt true, right? And the B part is if two variables are related by a line or curve of best fit on a scatter plot, does that means that one of the variable influences the other? I think no, because I would reject the conjecture as soon as the set of data I'm analyzing contradicts the conjecture, right? If the set of data contradicts the conjecture, that means conjecture is rejecting the data, right? If any data point doesn't match the conjecture, it cannot be because of the fully measurement, right? If I were to map the number of roads in Canada yearly to the x coordinate of a point and map the cancer incidence in that year to the y coordinate of a point, and then draw all the points, the line or curve of best fit would go upwards and to the right. This is because both values are increasing in the past 100 years, right? That means every year the length of the road is increasing and also the cancer patients are increasing, right? Okay, even though two values can be connected with a curve or line of best fit, it doesn't mean that these two values are related. Like these two values, the length of roads data 100 years and the incident, they are not related, right? Using the example, the number of roads does not relate to the number of cancer incidents. However, they both happen to have been increasing in the same period of time, right? So it is not necessary that the data must be related, right? Okay, let's just start with 6.5, describing situations from graph. Okay, in the problem involving movement, the graph shows displacement, distance, height, or depth versus time. Distance, sorry, distance, height, or depth is the dependent variable, and the time is independent variable. So we can say the velocity is this change in displacement divided by time. Determining the first difference in a table of values can be used to confirm if the graph represents a linear or nonlinear relationship. In linear relationships, the velocity is constant. A rising line indicates displacement increases as time increases. A falling line indicates displacement decreases as time decreases. A horizontal line indicates no change in displacement as time increases. In nonlinear relationships, the velocity changes with time. That is the explanation of the lesson. Let's just start with the practice questions. Okay, question number 4. A drag racer begins from a stop position and drives the length of a racetrack. The graph shows the distance from his starting point after each second of his run. A. Does the data represents a linear? No, that is a non-linear relation. Linear relation means the graph must be a straight line. This is not a straight line, so this is not a linear relation, right? Okay. B is verify your answer to part A by creating a table of values and calculate the first differences. Okay, you can just make a table of values and calculate the differences. Okay, for one, it is 20. Okay, let's just make a table of values and verify your answer. Okay, for 1 it is, for 0 it is 0, for 1 it is 10. Okay, let's just make a graph. I assume the values because the exact values are not given. If you have time 1, the distance is 20. Time difference, then we have to calculate the first difference. Time and distance, sorry. Okay, time is 120. Okay, for the second point it is 250, 300. Okay, for 4 it is 150. Okay, these are enough values. You can calculate the first difference. 50 minus 20, 30. 100 minus 50, 50. 150 minus 100, 50. You can see that first difference is not constant. That means this is not a linear relationship. For a linear relationship, first difference must be constant, right? Okay, the B C part is describe the motion of the drag racer as it moves down the drag strip to the finish line. So, describe the motion of the drag racer as it moves down to drag the strip to the finish line. Okay, so you can see time and distance is not constant, right? So that means when the runners does not drive at the same speed but gradually accelerates to the finish line, right? Okay, the D is if the drag runner racer crosses the finish line, a parachute opens to slow it down. Redraw the graph to show what this might look like as the drag racer slows to a stop. Okay, you can draw the graph on your own. Let's just start with the next question. Write a story of a graph. Okay, you are given the graphs, you have to write down the stories, like, right? Okay, question number 6 is what is poured into the container at a constant rate? Draw a graph that represents a situation where D is depth and T is time. What is poured into the container at a constant rate? Okay, you can see the depth of the figure. At this side, you can see the depth is increasing exponentially, like increasing, they are increasing. The depth is increasing exponentially, right? It will increasing slowly at the bottom and faster at the top. The rate of increase of depth will increase until it reaches the top part of the container, right? So the graph looks like the graph of the exponential functions, right? Okay, that's seven. Question number 7 is plot each set of data and then determine if it represents a linear function, linear or non-linear. Justify your decision. B part is in each set of data, determine if the object is accelerating, deaccelerating, moving at a constant velocity, or combination of all three. So you have to plot a graph for these things so that you can identify if they are linear relations or nonlinear relations, right? Okay, the first one, let me just calculate through first differences. I can see if they are linear or non-linear, right? So 9, 19, 20, 21, 22. The difference is 3. 22, 23, 24, 25. That's the first one is linear, right? Because they have the same, the first difference is same, so this one is the linear relation, right? Okay, just look at the second one. 35, 36, 37. You have 2. 37 and 138. The difference is not same. That means that is not a linear relation, right? Third one is, I think, linear. 0, 7. 16 minus 7 is 9. No, again, this is not a linear relation, right? We're just given 3, 4 points, and this is not a linear relation. Okay, then the B part is, in each set of data, determine if the object is accelerating, deaccelerating, moving at a constant velocity, or a combination of all three. The first one is linear, right? When the relation is linear, that means object is moving at a constant speed because they have the common difference, right? For the second one, the graph is non-linear. That means either it is accelerating or either decelerating, right? Okay, for the third one, the relationship is non-linear, right? That means either the object is accelerating or decelerating, right? Okay, okay, let's start with question number 8. A driver leaves at 8 a.m. and drives 120 kilometer by 9:30. From then until 10:30 a.m., she travels another 50 kilometers. She drives an additional 200 kilometers by 12:30 p.m. She travels at a constant speed during each period of time. Draw the distance time graph that represents the trip. What is the car traveling the fastest? When is the car traveling the fastest, the slowest? What type of relation is this? What is the average speed? Okay, let's just make the table of values. At 8, the driver leaves at 8 and drives 120 kilometers by 9:30. So from 8 to 9:30, the time duration is 1 hour 30 minutes, right? 1 hour 30 minutes means 90 minutes. So in 90 minutes, the time and the distance. In 90 minutes, the car drove 120 kilometers, right? That is the distance 120. Okay, then the next one is from then until 10:30. Okay, 1 hour more. So 90 plus 60 is 150. She travels another 50 kilometers. So 120 plus 50 is 170. So time is 150 and distance is 170. Okay, then she drives an additional 200 kilometer by 12:30. So 2 hours from 10:30 to 12, it is 2 hours. And 2 hours means you have to add 60 plus 60, 120, 120 and 270, and the distance is another 200. Oh, it is 270 and 100 plus 170 plus 200 is 370. That is the values, right? Okay, you have to make the draw a graph for A. B is, when is the car traveling the fastest and the slowest? Okay, That means in the third interval from 200 kilometers distance the car covered, right? That means that is the fastest one. And in from 120 just 50 kilometers, that is the slowest one, right? Okay. The next one is, what type of relationship is this? That is a linear relationship. What is the average speed of the entire trip? You have to calculate the average speed. Average speed is velocity is equal to distance divided by time. So the distance is 370 and the time is 4.5 hours, right? So it would be 82.22 kilometers per hour. That is the average speed of the trip, right? Okay, let's just look at question number 11. A, a race car travels around a racetrack. The graph of speed, the graph of speed versus the time of the first lap by the car is shown. What do the increasing parts of that graph represent? The decreasing parts. What do the horizontal parts of the graph represent? Using the graph, tell a story about the car as it makes its first lap around the track. Okay, the increasing part, they are the increasing parts. This one, and this one, right? That means the speed is increasing when the car is accelerating, right? And in the decreasing part represents the time when the speed is decreasing, thus the times when the car is decelerating, right? When the speed is increasing, car is accelerating. When the speed is decreasing, the car is decelerating, right? Okay, the horizontal part of the graph represents the time when the speed does not change over a period of time, right? Okay, using a graph, tell a story. Okay, so the car start accelerating. Okay, you have to start from here. The car start accelerating from the start until it reaches a set of curves, right? When it accelerates and deaccelerates at a time. So it accelerates, then deaccelerates, then again accelerating, deaccelerating, right? It then accelerates for the final stretch of the lap before reaching its top speed and driving constantly at this speed, right? Okay. Draw a graph of speed versus time as a car makes one circuit of each track. The arrows shows the direction of the car moving. Okay, for the A, you have straight lines in A, right? That means the car is at the same speed, right? That means the relationship is linear. Okay. Question number 17. Okay, Sheila takes a drive education course before applying for her driver's license. One of the topics studied in the relationship between speed and stopping distance. The instructor gives Sheila the table to the right. Graph the table using stopping distance at the dependent variable. Determine the rate triangle from 60 km to 70 and from 70 to 80. Okay, speed and the stopping distance, right? You are given. Graph the data using stopping distance. Okay, for the A part, you have to graph the data. For the B part, determine the rate triangle from 60 to 70 and 70 to 80. Okay, from 60 to 70. Yeah, that means you have to calculate this slope from 60 to 70, right? Okay, so the slope is from 60 to 70. Just use these two lines of data and calculate the slope. That would be 37.9 minus 28, 9.8, that is 8.1, and 10, that means it is 0.81. Same thing you have to do for 70 to 80, right? Now use these two lines, and then 47.5 minus 37.9 is 9.6 divided by 10, that equals 0.96, right? Okay, what do you notice about the rate of change in stopping distance as the speed increases by 10 kilometer in part B? That means if the speed is increasing by 10 kilometer by part B, the change in stopping distance also increases. You can see for 70 it is 0.81 and then it is 0.96, right? Okay, Sheila says, if I drive twice as fast, I just need to leave twice as much distance between my car and the car in front of me. Explain whether this is accurate. If you look at the data in the given table, the speed is increasing by 10 every time, right? That means if the speed is increasing by 20 kilometers per hour, that means the difference is increased then, right? So that means the relationship is not linear. So this observation is not correct, right? Okay, we are done with the chapter also and the lesson, but the chapter is too boring and I don't like the chapter because making this much graph in limited time is very difficult. Without making graph, you cannot write. So I am sorry if some of the points I skipped or some of the points you don't get right. So I'm sorry for this chapter. Okay, so we're working on grade 9 math. Chapter working on is investigating relationships. Lessons we have covered are reasoning about data and describing situations from graph. So please make sure before the next session you can complete all the test questions for the lessons we did today. So if you need more help with the lesson, you can contact any tutor on the Skype. They are available from Monday to Friday, 5 to 9, right? So that's all for today. If you have any question, you can please ask. So please ask if you have any question. Okay, that's all for today. See you in the next session. Bye, everyone.